Today we are walking through the paper titled Vision Pre-Training for Dense Spatial Perception.
What problem is the paper trying to solve first?
The paper targets dense spatial perception. That means a vision model should not only recognize what is in an image, it should keep the shape boundaries on geometric layout that later systems need for depth segmentation, video tracking, and embodied AI.
What was missing from earlier visual foundation models?
Earlier self-supervised models often learned strong image-level semantics, but dense spatial quality is usually obtained indirectly. The paper points to post hoc feature upsamplers, corrective regularization, and distillation from multiple teachers. Those can help, but they treat spatial precision as something to repair after pre-training.
So the paper changes the training target, not just the downstream decoder.
Exactly. The proposed model is called Lingbot Vision. Its central idea is boundary-centric mask modeling. During self-supervised pre-training, it finds image boundaries online, forces boundary-bearing patch tokens into the mask, and trains the model to reconstruct useful representations at those difficult spatial locations.
What does boundary-centric mean in the actual training loop?
It starts from a teacher-student self-distillation setup. The teacher is an exponential moving average of the student. The usual semantic branch matches class token and patch token distributions across augmented views. But this paper adds a boundary branch so the dense tokens near shape discontinuities become part of the learning signal. The first formula defines the moving average teacher. The teacher parameters are updated from the old teacher and the current student, so the target changes smoothly instead of chasing every noisy student update.
Why does the teacher need to move slowly?
A slow teacher gives stable targets. The paper later uses that same stability idea for boundaries, where naive continuous regression can rift and collapse. So the moving average teacher is the backbone of both semantic self-distillation and the new boundary supervision. Now look at the boundary forcing step. The paper defines boundary tokens as patch positions intersected by predicted boundaries, then adds those positions to the normal random mass. This makes the student reconstruct exactly the places that carry object contours and surface breaks.
Does that mean the method already needs good boundary predictions at the start?
That is the chicken and egg problem the paper handles. At the first step, the model cannot already know boundaries. The authors use lightweight corner points on image gradient orientation to produce usable early line fragments, and those targets sharpen as training continues. This method visual shows the training idea. The input image is converted into teacher patch features. Boundary tokens are selected, and similarity maps show that the learned tokens carry both semantic grouping on geometric structure.
What should I compare inside that visual?
Compare the selected boundary tokens with the similarity maps. The point is not just that the model detects lines. The queried boundary tokens activate coherent parts of the scene, so the representation links local edges with object-level grouping. The cube sequence makes the masking change easier to see. With random masking, hidden patches can land anywhere. With boundary forcing, the masked regions concentrate on the surface edges where geometry changes.
So boundary forcing changes where the hard reconstruction questions are placed?
Yes, the mask still includes random patches, but it also guarantees coverage of boundary-bearing tokens. That changes the lesson the model receives. Do not only be invariant to clock changes, also reconstruct the local structure that tells surfaces apart.
How does the paper avoid unstable boundary regression?
The boundary field is first a continuous map around line segments, with values such as distance and direction. Directly regressing those values failed in the teacher-student loop. The paper turns each boundary field channel into categorical bins. So the same centering and sharpening tricks used for semantic distillation can stabilize boundary learning too.
What evidence shows the method is not just helping geometry while hurting semantics?
The small-scale proof of concept compares a VOICEVOX model on ImageNet 1K against a matched DINO plus IBOD baseline. The full recipe raises ImageNet K nearest neighbor top 1 accuracy from 81.6% to 80.4%. Improves NYUV to delta 1 from 81.4% to 84.9%. And lowers NYUV to RMSE from 0.47 to 0.40.
That result matters because both global semantics and dense depth move in the right direction, right?
Right. If boundary supervision merely over-specialized the model, classification would suffer. Instead, this ablation says semantic recognition and dense geometry can improve together when boundary structure is part of the pre-training objective.
What happens after they scale the method?
They scale the same method to roughly 161 million curated images. On dense visual tasks, Lingbot Vision is strongest where spatial structure matters. It achieves the best NYUV to RMSE among the compared models, ahead of the 7 billion parameter DINOV3. And on semantic segmentation it beats equal size DINOV to by at least for MIO, U on 80E20K. Sitscapes, and VOC12.
Does the paper show the same pattern for video, where consistency over time matters?
Yes, for training free video objects augmentation, Wingbot vision reaches 70.0 on DA, IS and 73.5 on YouTube VOS. That is close to DINOV3 VITH plus and DINOV3 7 billion, and at equal size it beats DINOV2 by 6.1 and 7.9 points.
The title mentions dense spatial perception, but the paper also discusses depth completion.
Depth completion is the paper's downstream test asked for geometry. Wingbot depth to point thorough keeps the mask depth modeling recipe from the previous system, but swaps in the Wingbot vision encoder and scales the curated RGB data from 3 million to 150 million samples.
What concrete depth completion improvement does the paper report?
In the encoder isolation study, using Wingbot vision instead of DINOV2 or DINOV3 improves nearly every benchmark, with a large block mask gain on D, IOD indoor, 0.09 for MSE versus 0.152 against DINOV2 at VTL, and 0.083 versus 0.118 at giant scale. Then, in full depth completion, Wingbot depth to 0.0 gets the best RMSE on 7 of 8 masking pattern benchmarks.
Were there cases where the improvement is especially visible?
The paper highlights hard missing depth cases. On block mask DIOD indoor, RMSE is cut from 0.13 to in Wingbot depth 1.0.06 to inversion to 0.0. On DIOD outdoor, it improves from 3.40 for 2 to 0.440. For real sensors, version 2.0 is best on 6 of 8 camera configurations and is especially strong on transparent object clear glass captures.
What is the fairest takeaway from all of these results?
The paper's claim is not that boundaries are only line segments. It argues that boundary modeling is a scalable pre-training principle. By making boundary-bearing tokens part of the reconstruction target, Wingbot vision learns features that remain useful for semantics while giving stronger spatial structure for depth, segmentation, and video.
So the main lesson is to train the backbone to care about the places where geometry changes.
Exactly. Instead of repairing spatial detail after the fact, the paper puts boundary structure into the pre-training objective itself. That wraps up this paper walkthrough.